Good afternoon, everyone. My name is Yifang Liu from Oak Ridge National Lab. I will be presenting our work on developing our lab scale prototype of a cable-driven parallel robot, or CDPR, for automated installation of prefabricated building envelopes. This is a joint work with my colleague Nolan Hayes, Balaji Selvakumar, Diana Hong, and the PI of this project, Brian Maldonado. So in the US, more than half of the residential buildings were constructed before the 1980 building, the established of 1980 building code. This means this building will either have low or no thermal insulation. And this building will have a large energy loss and also a higher energy bill. So this has a very big impact for lower income households. But how to resolve this? So overclad panel envelope retrofit are one of the most effective way to improve energy efficiency in buildings. How this works is that we first get the dimension of the building, and then we design this prefabricated panels that can be installed to the building's exterior. Once these are installed, and the updated envelope will lead to 17 billion savings in energy bill. This is a huge deal for low income households. Currently, how a prefabricated panel is installed is right now is largely rely on human labor, as shown in this video. And this process usually involved, if there would a team of construction workers, they would rent a crane and cherry pickers, and then installation crew will use walkie-talkie to communicate with the crane operator to basically give the crane operator instructions on to move left, right, or up or down. So they will try their best to install these panels to the building. However, you can imagine that this process is slow, and you usually, depending on the size of the panel, usually each panel requires like at least 2 hours installation time, and this is also labor intensive and error prone because they don't have a good way to estimate the position and orientation of the panel. So we know that error compounds, and at some point maybe they cannot install the next panel anymore because, for example, the window wouldn't align. They have to rework. This would cost more money, more time. So we know that the accuracy and speed can be improved through robotics and automation. So our solution is to use a cable-driven parallel robot for automatic installation of prefabricated panels. We chose CDPR because, first of all, they have a small footprint. This is extremely useful, especially for densely populated area, for example, New York City. And they also have a large payload capacity because most of the time these panels are heavy, and they are flexible in configuration, which means we can attach the cable differently than the normal case. So essentially, CDPR manipulates this end effector. Here, in our case, is the panel by winding or unwinding the cable. Basically, we want to change the length of the cable in order to change the pose of the panel. And here, this is a sketch is our full-scale rendering, and we can see that this here is a multi-story building, and we use a total station to estimate the position and orientation of the panel, and it has like 8 cables. So this is our lab scale prototype in a safety enclosure. In the middle, that's the end effector. You can imagine that that's the panel, and we have 3 prisms installed on the inside the panel, and then this 3 prism define this rigid body. And when the end effector is in stationary, and we can use the total station to cycle through these 3 panels so that we can get position orientation of this end effector. However, when the panel is in motion, we cannot use this to cycle through these 3 prism. What the total station can do is like lock onto one of the prism and keep tracking. So the way that we estimate the real-time orientation is that we also attach a wireless IMU, basically provide us a real-time orientation of the panel. And as shown here, we have like 8 cables connecting to the end effector, and each cable connecting to one of the actuation system as shown here on the right. And then we have each actuation system has a motor, gearbox, and torque sensor that provide torque feedback, and also we have drum and pulley to guide the cable. So here this slide shows 2 demonstrations of the system in motion. The first one you will see is it will move along a 3D diagonal trajectory. It will start from a lower position, move to a slight higher position. At the same time, it will move away from you, which means it will move towards the back of the robot. And we also have this total station. Well, you will see that while this is moving, and total station is also like kind of rotating along with the end effector and try to lock. We can obtain the position continuously. On the right is a similar movement, but it basically is a vertical movement. Right. So we designed the system from scratch. Basically, we start from 0, and then this is how we put everything together from left to right. We use total station and IMU to estimate the end effector pose, and then we use a router as a communication center hub, and we also have a Ubuntu system that running ROS that runs high-level control, and inside the control cabinet, the core is the trio motion controller. Basically, it does the low-level drive control, and we basically implemented some basic functionality. For example, we want to move the encoder to the desired position, and we also want to be able to jog. And the most importantly, we have this torque and the encoder safety limit to safeguard the system. We also have a human-machine interface that allow us to monitor the state of the robot. At the same time, we can jog each individual axis. The basic workflow for the robot is to follow a path to bring the panel to the desired location. The first step is that we run resection algorithm to establish transformation between robot and total station. The reason why we do this is that we want minimum restrictions on the total station, because in construction site it might be unstructured, so messy. As long as the total station has the view of the building facade, that's a good spot. How resection is done is it look at this 4 control point, fixed control point on the building, and measure their position and compare this control point with the digital twin, so that we can build the transformation. And then we can pre-plan reference trajectory, and then the robot will conduct a trajectory following. In the end, the total station will measure the position and orientation. But in this paper, we use torque PI control for trajectory following. This is a diagram for the torque control. Essentially, we measure the shaft torque. We get the difference between the shaft torque and desired torque, and the difference fed into the torque PI control, and then it generates the desired encoder position, and then we fed this into the drive controller. Then drive control will take care of the movement. The controller basically adjusts the cable tension in real time to move the end effector accurately along the desired torque trajectory. On this slide, we show that the robot can successfully follow the desired torque. We show this the two trajectory. On the left is a vertical trajectory, and on the right is a little bit complicated. Basically, it starts from one location, it travels through a rectangle trajectory in 3D and come back to the initial position. And in the plot, the orange line represents the desired torque, the blue line represents the measured torque. We can see that the measured torque follow the desired torque tightly. So we use torque controls. That's why we don't use position as a feedback, and so that's why position has a larger arrow. Here we show 4 trajectories, and you can see that somehow they can follow the plan, the model of the position, but in the end there's some sort of arrow. Sometimes you will see a larger arrow in between during the trajectory. The major takeaways are we learned that torque control alone isn't enough for precise panel placement. We really want to incorporate position feedback, like we can use the laser tracker and IMU to improve the system accuracy. Luckily, we already have this all these 2 sensors integrated in our system. Our future work will be now working on this more sophisticated control algorithms. So our method doesn't stop at only at this panel installation for retrofitting. You can imagine that they can also be applied to new construction and other facade related work. For example, it can actually spray air barrier membranes on the building facade. All right, thank you for your attention. If you have any question, feel free to drop me an email. And our team actually is hiring. If you are interested in construction robotics, feel free to scan this QR code and check out our job posting. Thank you.
Do you have any questions from the audience?
Yeah.
Thank you so much for a nice presentation, very interesting work. Are you planning to do an actual implementation of this on a real project, or are you sitting at the lab level for now?
That's the plan, but it also depends on whether we have the funding.
But do you have any particular project in mind that you could implement this technology? Or maybe the developments that you're doing, are they geared toward a practical application or more theoretical and lab based?
It's gonna be a application. We are currently looking for, right now we are developing this lab scale prototype, and we are looking for opportunities to deploy this in the real world, and hopefully we can find some industry partner or some yeah.
Thank you.
Yeah. Thank you.
Questions? So thank the presenter.